What you are about to see is a computation that should not be physically possible in our current understanding of time. Engineers have identified a specific mathematical problem so complex that solving it with the world's fastest supercomputer would take 10 septillion years. To put that in perspective, the universe itself is only 13.8 billion years old. If a standard supercomputer had started this task at the moment of the Big Bang, it would be less than a fraction of a percent finished today. Inside a laboratory in Santa Barbara, Google's newest quantum system, Willow, processed that exact calculation and reached the final answer in just 5 minutes. In those 300 seconds, the traditional relationship between computational power and the age of the universe was rendered irrelevant. This photo shows how we used to solve this, by expanding. Traditional supercomputing power is tied to physical scale, acres of server racks requiring massive amounts of electricity and floor space. But the Willow chip doesn't need a warehouse. It requires a different kind of extreme environment, a cryostat that isolates the processor from the rest of the world. You can see the industrial cryogenic tanks used to achieve this. To function, the chip must be kept at 10 millikelvin, a state colder than the vacuum of deep space. At these temperatures, the heat that normally vibrates atoms nearly stops, allowing the chip to manipulate matter at the subatomic level without interference. Standard computers speak in binary. Think of a normal bit as a coin lying flat on a table. It is either heads or tails, a 0 or a 1. It cannot be both. A qubit exists in superposition, like a coin spinning on its edge, occupying heads and tails simultaneously. This allows the machine to explore massive fields of solutions at once. Classical computers check one path. The quantum system processes the entire mathematical landscape exponentially. This doesn't make your desktop computer obsolete for daily tasks, but for the specific heavy mathematics of molecular biology and cryptography, classical logic has reached a performance ceiling. Despite this potential, the technology stalled for 30 years because of decoherence. These quantum states are so fragile that even a single stray photon can cause the qubits to lose their information and crash. This created a paradox. For decades, adding more qubits to a system only made it noisier. Instead of getting smarter, the machines became more prone to error, failing before they could complete a single useful task. It appeared as though the physical noise of the universe would prevent a large-scale quantum computer from ever becoming stable. Google's recent breakthrough uses a system called surface code error correction, utilizing what they call distance 7 logic. This chart shows the error rates as more qubits are added. Historically, the line goes up, but when distance 7 logic is applied, the more qubits you add, the more the error rate actually drops. It's a method of using a group of noisy qubits to act as one single perfect logical qubit. It is the exact equivalent of hearing a whisper perfectly clearly, even while standing inside a chaotic, screaming crowd. By proving that they can reduce errors by scaling up, Google has moved quantum computing from a theoretical experiment into a functional tool of engineering. The goal is to scale this error-corrected architecture from dozens of qubits to 1 million. Modern digital security, from your bank account to government secrets, is protected by prime factorization. It is a mathematical barrier that would take a standard supercomputer thousands of years to solve by guessing one number at a time. A million-qubit system uses Shor's algorithm to find those factors in minutes, rendering current encryption ineffective. This means that any data encrypted today, medical records, financial transactions, and classified communications, could be read as easily as plain text once these systems are online. The mathematical difficulty protecting the digital world for 40 years is nearing its expiration date. Will we use these systems to solve molecular puzzles of disease and clean energy, or to end the era of digital privacy forever? Subscribe to Zero Logic for more deep tech documentaries exploring the hidden systems shaping our future. Comment below, would you trust a world where your privacy depends entirely on quantum-proof logic? As always, stay curious and trust hard logic.